אז ג'רי ספר לנו היום על קליפ אדפטרס. היה איזשהו רצון כללי פה להציג את הנושא של אדפטרס. אני חושב שגם דיברתי עם דן וכאילו נתקלים בזה מכל מיני כיוונים. שי בעצם אנחנו ראינו את העבודות על ביט אדפטרס שימוש מאוד דומה, אבל למטרה אחרת לגמרי. הדברים פה יותר קשורים למחקר של ג'רי, אז הוא נתפתח אחר.
Hello everyone, good afternoon. My name is Jerry Ayub. I'm a master's student with the Simon's Group. And today, as I said, we'll be tackling the subject of clip adapters. But what we'll be doing today is we're going to tackle the clip adapter in the few-shot setting. So first, I'm going to talk about what is few-shot learning and talk a bit about the settings over there. And clip has already been presented here, but it was so long ago, so I'm going to recap a bit about clip, how was it trained and what is it used for, and how we can use adapters with clip to enhance few-shot classification performance. So first of all, we're going to talk about the settings of few-shot and what is actually few-shot learning. So the bottleneck of classical supervised learning pipelines was the amount of data it needed. So if we take, for example, ImageNet, which is a basic basis for for all of classification tasks, it has a lot of data and a lot of classes. But in the real-world scenario, that's not the amount of data is really limited, and that's not the ideal setting. So in a typical supervised setting, we have a data set and we have splits. We train it on the training split, and then we test it on the test split, and we know that the test split and the train do not overlap. So they're distinct splits. And we need to optimize a set of parameters such that we minimize a certain loss function so that it has the best performance on the test set. Okay, so the few-shot learning is a central problem in computer vision. It's not only tackled in computer vision, but what I'm going to talk about here is specifically the computer vision part of few-shot learning. And by introducing this limitation, it becomes much harder to solve by foundational methods, and we need to tweak things around a little bit and present additional improvements. Let's talk about the setting. I'm just going to say this is one of the settings to tackle few-shot learning. There are multiple other methods or multiple other settings, but this method is called episodic training or task training, where we can think of a task as a certain batch, and every batch has a support set and a query set. So the task, like I said, it has a support set and a query set, where the support set is a supervised set. So we have the labels during the training, and we get the queries as an unsupervised set. And the notations for that is K-shot and N-way training, such that K-shot means that we have K samples from each class, and N-way is just the number of classes we have. So if we look at the illustration on the right side, every task, we can see that it has T1, T2 until TK. The support set here is the one on the left. So the train is, if we look at the first task, is dogs and cats. We have 4 shots from dog and 4 shots from cats. We have 2 classes and 4 samples per class. So it's 4-shot, 2-way setting. And we can see that each task has a different class from the data set. It's not, it can't be the same classes in each task. And our task is, when we get the right side of the figure, we need to classify if it's a dog or a cat, and no one cares how, just we need to classify it correctly. So all in all, we have k times n labeled samples. That's the support set. And we also have the query set that we need to classify. All in all, sometimes we can also take the query set as an unsupervised set and use it during the training. We will talk about the setting as well. So we have, let's say, n times k plus q samples all in the task. Sometimes the q can be 0, but we can assume that it's not. So the first algorithm I'm going to talk about is called prototypical networks. It was presented in Europe in 2017. And if we look at the illustration, we can see, sorry, we can see that the support set here, here specifically, it's 3-way and 3-shot. So we have bird, snake, and dog classes. We have 3 samples from each. And of course, we have a neural network. We call it an encoder. So an embedding network, it can be a convolutional neural network, a ResNet, whatever we want. And our task is, given the input query, we need to classify it depending on the classes that we have. So over here in the illustration, the input query is a bird. So we need to classify it as a bird. And prototypical networks work in a very simple manner. Since the support set is labeled, we have the actual labels of the embeddings. So after we push them through the encoder, we have a couple of vectors in an embedding space with their respective labels, and we can use these labels, to do something with it and maybe cluster them together or whatever. So we have 3 shots over here. Let's say from the bird, let's look at the blue zone. We have 3 embeddings from the bird, and we apply k-means on those 3 vectors, and we get a centroid. They call it a prototype over here, but it's simply k-means. And so given an input query, we need to measure the distance between this query and the other prototypes. And with a high probability, we can say that the closest distance is the class, let's say the closest distance between the input and the centroid is actually the class that it's supposed to be.
Why do you say k-means? Because there's no sort of clustering here, like all the labels are known, right?
All the labels are known, but how else can you? Okay,
you
so
mean the computation of the class centers?
Yeah. Mm-hmm. It's not specifically k-means, right? We can just take the average of the embeddings. Mm-hmm. And so after that, we take the distances, we calculate the probabilities, and we make the prediction. So as I said, we can use a CNN network architecture. Usually in few-shot learning, in these settings, they use either a 4-layer convolutional neural network or a ResNet 12 or a ResNet 18. Also, sometimes they use a wide ResNet 28 as an embedding function. And then the prototype for each class is defined by taking the average, like I said. So if S over here is the support class images, we simply take the sum of all of the embeddings and divide it by the number of them. And in order to calculate the similarity between the query and the centroids, we need a certain distance function. Distance functions that are used over here are a cosine. We can use cosine or the Euclidean distance, but in prototypical networks, they usually use the Euclidean distance function. And that is done for each query. And we simply can apply softmax on the distance function between the encodings and all of the prototypes. Softmax that gives us a distribution. And the last function that can be used here is the negative log likelihood, and we can minimize that in order to get the correct prediction. So
what is trained here? What is?
We have the support set for, let's say, bird, snake, and dog. This is given to us, okay? This is called the support. So we take k-shot and k-shots from n classes, we have the labels for that, and we put them to the embedding network, and we can take the sensors from them.
So you're training the Resonate 18 or something like that too?
Yeah, you can do that, but I was just about to say that prototypical networks can be used on a pre-trained backbone as well, because this is not trainable. So this is a non-trainable method. We can apply that on a pre-trained network as well, but you can use that as well in order to get stronger embeddings and even train the network as well. Yeah, that was what I was about to say. Now, few-shot learning was used as a method to evaluate meta-training approaches and their performance, but we all know that learning to learn is not the only strategy. Transfer learning is a strong competitor, where the few-shot samples are used to learn or construct a classifier given a pre-trained feature extracted. So this paper posed two main questions. So how do different backbones affect the few-shot learning pipeline that we just defined? And in other words, are vision transformers better suited for few-shot learning? And if so, how does the pre-training regime affect the few-shot learning pipeline as well?
But here you mean, what do you mean this regime? So instead of training the meta-learning approach, you first train a classifier and then you fine-tune it on the
Using the
few shots you have.
Yeah, exactly.
So there's no prototypical.
No, we can use the prototypical here to fine-tune the backbone as well. We leverage the pre-trained knowledge, and we can use the prototypical setting in order to fine-tune the pre-trained backbone that we have.
You don't fine-tune the classifier, you fine-tune it as an embedder.
We fine-tune it as
You use a pre-trained classifier to generate embeddings for the prototypical network. Then you fine-tune it on the. Okay, so you fine-tune it in the way you train the prototypical network.
Yeah. So for example, in this figure, we can see the blocks, the blue, orange, green, and red blocks. These are the previous meta-learning approaches using the CNNs and the ResNet backbones. And this is tested on the mini ImageNet dataset, which is a dataset extracted from the ImageNet, the traditional ImageNet dataset, but for the few-shot learning setting. And this is tested on a 5-shot, 5-way setting as well. So these approaches achieved, let's say, 90% on a 5-shot, 5-way task, whereas the new transfer learning method, the yellow star that we have above, it uses a vision transformer with a pre-trained self-supervised dyno on ImageNet, and it was fine-tuned with a ProtoNet classifier on mini ImageNet. And this achieved an even better result.
So, but the dyno was pre-trained on ImageNet, where mini ImageNet is a subset of ImageNet. So in some sense, it has seen these classes.
Yeah, it's for sort of cheating.
Yeah, so that class information. It's not dyno is unsupervised.
The dyno it was not
but
specifically mini ImageNet classification.
if it's seen this data before, it's kind of a different, I'd say, category.
So if we look at the results, we can infer that the backbones really do make a difference. So without pre-training, which is the orange and red box, I don't have the cursor over here, but you hope to see it. Large networks don't work so well without pre-training. And pre-training alone gives us comparable or better results than the classical prototypical networks, which is the blue box above. And combining pre-training and prototypical gives a huge boost for the performance. But it seems says that yes, large networks do affect the few shot learning on the few shot learning pipeline. And the second question to be posed is vision transformers better suited for few shot learning? And here they check two different vision transformer networks. There's the vision transformer small and the base, which is a larger network. And we can say that vision VIT small is much better than ResNet 50. And even larger vision transformers are better with suited pre-training. So yes, the backbones do make a difference on our setting.
Is it connected to the type of the specific data set that you test on the few shot classification? Because
Dyno was pre-trained on images, right?
Mhm.
So they also check that on CFAR few shot, and it does get better performance as well. So it's not only data set compatible, can also generalize to the other data sets. That was the question, right?
yeah, but also like sounds like a conclusion that's related to I don't know. It should depend on the size of the or how these tasks are defined. I mean, how many classes you have, how many shots, or size of the data set, and to come to a conclusion like which size of the architectures are suitable or not.
Let's say that no, the experiments that they did was only using the ImageNet pre-train, but we can say that ResNet also doesn't have. Also, ResNet's pre-training was not on ImageNet, right? But it was a different, training pipeline. So, if I recall correctly, even when they generalized the experiments to other data sets, even if the tasks differ a bit, it did bring better results. But they also compared their stuff to meta-learning approaches, whereas here it was tackling a transfer learning approach and not a meta-learning approach. So maybe that also makes a difference. So until now, we only talked about classification few shot learning tests. The supervised, semi-supervised classification uses, for example, few shot learning examples, and we need to label the given unlabeled examples and improve the few shot classifier. So we have, like we said, if we have the support set and the queries, we have a supervised set, and we also have an unsupervised set, and we need to classify the text data. Where unsupervised few shot learning is we don't have any labels or we don't have any support at all, and all the samples are unlabeled. We also have something that's called transductive few shot learning, and that's where we jointly predict all the query examples along. That's where we jointly predict all the query examples, so we can take a look at them, how they're plotted in the latent space or in the embedding space, and we can infer some stuff about it over there. But few shot learning is not only classification. There are also other tasks such as cross-model few shot learning. So all of the pipelines that I talked about until now, they were unimodel approaches, and some recent approaches employ data from a different modality, like text, for example, and where we can combine information from an image as well and its label word embedding to develop a better prototype of its class, for example, using the prototypical network. We also have generative few shot learning. One usual way one way thing to alleviate the problem is learning from low data samples to augment them with synthesized samples. And but there's a big problem with generative few-shot learning, and that's hallucinations. And they address that problem with hallucinators, and it maps real examples to hallucinated generated samples, and they try to make a connection between them. And one of the nice applications of generative few-shot learning is when our data is very limited and we need to expand the data set. We can apply this technique to even expand the data sets and have even larger data. Cross-domain few-shot learning is the approach where we need to recognize any novel categories with only a few labeled examples of each class. And one assumption that was followed was that all few-shot tasks belong to the same distribution or domain. For example, most approaches sample tasks from mini ImageNet during the training as well as testing. While promising results were observed following this assumption, this existing method often failed to generalize to unseen domains. And maybe that's what you told me before. I remember you've seen ImageNet and maybe you failed to generalize to other datasets. And this is the problem. This problem of few-shot learning under domain shifts is referred to a cross-domain few-shot learning. And this is just like tell you few-shot learning is not only classification tasks, but what I'm going to go into right now and for the remainder of the presentation is zero-shot learning and what we can do with zero-shot learning. So zero-shot learning is where we have no labeled data whatsoever at inference, but class names are available to compare with when we want. Because if we don't have the labels, it's just unsupervised clustering. Okay, so zero-shot learning, we attempt to solve a task without the presence of any training examples for that task, but we need to leverage some sort of pre-trained encoder. So for an image classification task, zero-shot learning methods rely mostly on visual auxiliary model alignment, and oftentimes the auxiliary data is image labels. Okay, so the samples for the same class or from two modalities are mapped together so that the two modalities attain the same semantic structure. And we will see how Clip does that in the next slide. And because zero-shot learning does not have any access to any visual information when learning new concepts, zero-shot learning models have no choice but to align the two modalities. So this way, during the test for the image query, let's say, this can be directly compared to the auxiliary information for performing the classification. And one of the most powerful tools that we can use such setting is the model Clip from OpenAI because of the joint embedding space. So it maps the visual embeddings and the text embeddings to the same space, and therefore we can learn any semantic relationship between the two modalities.
Can you give an example of zero-shot learning?
Yeah. This is all we're going to be talking about from now. And okay, so let's recall what is Clip and how it was trained and how it can be used. We already talked about that in the groups over here, but it was so long ago, so I'll make a recap. Okay, so in 2021, OpenAI released the paper titled Learning Transferable Visual Models from Natural Language Supervision, where they introduced Clip, a state-of-the-art multi-model that connects images and text in a shared embedding space. Okay, so that's the key here. It's the embedding space is shared for both the images and the text. And they're not the first ones to do that, because before Clip, there were several multi-models that that attempted to connect the text and the image embedding spaces. But Clip was the first one to scale this alignment using the contrastive learning on a very large base. And while standard image models jointly train image feature extractor and the linear classifier to predict some label, let's say some class, Clip jointly trains an image encoder and the text encoder together to predict a pairing of a batch of image and text. So the training here is very different from what we're used to.
But they froze the text, right?
Sorry?
The training, they didn't change the text, they only changed the image
I
encoding.
don't think that they changed anything. They changed the text.
No, during
Okay.
training the weights, where they were only training the weights in the image encoder, not in the text encoder.
Both.
Both,
No, I think it's both. And since
But-
Clip was,
you sure?
Yeah, they have to be also mapped to the same domain, to the same space.
To map to the same domain to the same space, you don't need to change it.
Right.
Actually, they have people talking about that if you change both of them, they keep chasing each other. So you have to freeze one so that the other will adjust to it.
But there's this contrastive training scheme which
Like
usually,
one space is fixed and the other moves to it. Like you don't need to move the two of them.
yeah, no, agree that not necessarily, but as far as I recall,
yeah, they changed.
they train better together here.
I'm a bit confused. Are you talking about changing text or changing the weights?
The weights of the text encoder and the
Weights of
image
the text.
encoder.
No, I did change both of them. Sorry.
You could maybe freeze one at a time.
So they're doing one at a time, maybe?
I don't think so. Like, I didn't read that in the paper. But so Clip enables a very powerful zero-shot classifier without being explicitly trained on the target labels. And the question is, why is that? And it's because the learned text encoder can classify the embeddings of the target's dataset classes based on the embeddings of the names and descriptions that it was trained on. So it was not trained on explicit classes. And so it has much more information inside.
In the loss function, the classic loss, what is the positive classes and the negative classes then?
So I'll be getting that just in the next slide, but really I'll say that it's the similarities. Let's say this is a batch over here. I don't have my cursor, but that if you see the green block on the left figure and the purple block on the above figure, this is a batch. Okay, so we have n images and text, and we know that T1 aligns with I1, let's say. And we get this matrix, and we need to maximize the similarity in the main diagonal, and we need to minimize the rest. Okay, so basically the last function does that. Okay, so as I said, the training here is on the similarity between the image and the text embeddings, and it was different from previous methods because all of those methods relied heavily on natural language supervision. Okay, here we don't need that really. And the image encoder here has many, they tried many image encoders, but basically it's just a vision transformer or a ResNet network. And the text encoder is a BERT or GPT style. And as I recall, that even the text encoder is not that large, it's like 16 layer, it's a 16-layer transformer. And they both map the embeddings to the same space. Okay, so we can compare with them directly using cosine or any other distance function. So the Clip is so strong because it was trained on almost 500 million, more specifically, it was trained on 400 million image and text pairs. And the new loss function over here is called the info NCE loss. and it encourages the embeddings of the text and the image to be similar. Instead, in this, if we compare like using the matrix, we need to maximize the main diagonal and minimize the rest. Okay. So since we're talking about similarities, as our batch size gets bigger and we get more comparisons, and as it converges to the dataset size, it means that we learn the representations better. So if I also recall correctly, the batch size that they used in CLIP was 32,000. So we need a large batch size in order to get as many comparisons as we can. And after computing the dot product, we can apply softmax on the rows alone and on the columns alone to get different viewpoints of the distributions. So how each text embedding compares to all of the images and how each image compares to all of the text embeddings. And yeah, and we can use that.
And then inference, how does it work?
And
Do you
I
have
think,
fixed classes or is
okay,
it generate
yeah.
description?
So in inference time, in zero shot prediction, if we get, for example, this image over here, the bottom right, we push it through the image encoder, and the text over here, let's say that we're predicting for a certain class. Okay, like I said, zero shot was not CLIP was not trained explicitly to classify in classes. It was done on certain text, so descriptions. So we can apply a certain pre-process regime on the classes that we have. So instead of getting plane, cat, dog, bird, we can say that it's a photo of a plane, a photo of a car, or a photo of a bird. And we after we get all of those embeddings from all of those classes, we get also the embedding of the image, and we use the cosine similarity and assign it to the closest one that we get.
Could you use the location of the image to actually generate the description, or is it not?
No,
the location,
The
we
embedding space location, the image, to generate the description that sits on that.
so it's related maybe to the co-op
yeah.
work
that's- okay.
that I think you're
Yeah, okay.
mentioning, right?
So now I'm gonna say no, but in a bit we'll see a paper that improves upon that.
I don't think they changed the text.
In training,
Exactly, because they say in the paper, in the training, they say we train a series of 5 ResNets and 3 vision transformers. Like the text is a non-issue, like they don't think of it as something that is trained. Like they only fix the text encoder, we only scale the width of the model to be proportional to the calculated. Like they add like a little layer at the end. So that the dimension could fit.
train only that.
So that they could, yes, they train that, but
So they don't train from scratch, but there is some training.
I think they don't train anything. The vision is initialized with a vision transformer.
And
But they train it after it's initialized, but
vision transformer is an architecture. It could be
but it still has the weights, like the initial weights that was.
yeah, so that's something we have to check out, but
The reason I have an opinion is because we did a similar idea for sequences and structures in proteins. And we fixed the structure, like we only changed the, like we think of it as infusing the sequence encoder with structure information. But people talk about the CLIP as infusing vision transformer with semantic knowledge. Like the infusing business means that the one of them is changed and infused and the other one, no, this is not the subtext of this statement.
It's not clear that it's ideal to keep to bring the images to the domain that was chosen for text separation. I'm just thinking
No.
about it, I don't know what, so I'm not sure exactly what they do in that sense, but what I thought is that they train both, maybe they initialize both in some.
No, the initialize goes without saying, but like, of course, you don't start from scratch, but they get makes
I'm
those
not,
next-
I'm not sure because it's a very serious training on a lot of data that takes a lot of time.
Yes, they write 5 weeks or something.
Yeah, so I wouldn't be surprised if they might as well try to train from scratch, but yeah, I'm not saying that from knowing what actually happened.
I think if they actually freeze, you're saying that they actually freeze the encoder, the text encoder. Yeah, that's
We were wondering, so.
Exactly, like I'm trying to figure this, like I care about this corner.
okay.
Why not?
Yeah, so we have some work.
Okay. So the last function is called, as I said, the info NCE, and it basically we insert over here the cosine distance between the image embeddings and the text embeddings. So if xi is the image embedding and yi is the text embedding, and n is the batch size, we have two loss functions because we have two different viewpoints, okay? One from the text perspective and one from the image perspective. So from image to text, it's the same loss function, but with different values. So we have exponential like cosine, the similarity between the image and the text, and alpha over here is just a temperature parameter. It's actually learnable. So it's like softmax over here, but on the similarities. And the loss from the text to the image, the only difference over here is I just wrote that, but I missed it. This over here is the same one, but they have different values. So these two loss functions are not the same. We get the similarity between the image and the text, and just basically just the softmax. Oh, you don't see my cursor, sorry. The inside the log, we have just the softmax of the similarities of the similarity distances. And because we have different values, or we have different perspectives, the distribution is different from the text point of view and the image point of view, we sum those two losses and we multiply by, or we divide by 2. Okay, so that's the loss function. And the alpha over here actually you're wondering what alpha does. What is this hyperparameter for? It controls the sharpness of the softmax. Okay, so those are examples from the CLIP paper for few-shot inference. I'm going to read them over here because you don't not readable. So, for example, okay, I'm going to say that this is taken, for example, the first photo was taken from Food 101, the second is from Sun 397, and the last one is from facial emotion recognition. Okay, so this is zero-shot inference, and we know that CLIP was not trained explicitly on those data sets. Okay, aside from those, there are many more in the paper that they showcase. But we can clearly see that it could classify the guacamole from Food 101 and the television studio with high confidence. So in the Food 101, it says a photo of guacamole, a type of food. Okay, and Sun, it says a photo of a television studio. And over here, they showcase the top 5 competitors, and with high confidence, almost 90%, it classifies the images correctly. But we can see also at the facial emotion recognition, where it's orange, it didn't classify it correctly. So with high confidence, it said that it's a photo of a happy-looking face, but in reality, the grand truth label is that's a photo of an angry-looking face.
Just to clarify, the few-shot classification problem here is you're given the names happy, neutral, surprised, fearful, and angry.
This is
The names of the classes, and and given this image,
but no, this is zero shot inference. It's not.
yeah,
few shot.
so that's given the names of these classes.
If we transform it into a few shot setting, you think?
This is zero.
The zero shot
Oh.
setting, yeah, so you're given one of the 5 names of the classes, happy, neutral, surprise, and so on.
No, but it has many more. It has many more classes. So these are the top 5. These are the top 5 that it classified with high confidence. But Food 101 has 101 classes. So it takes 101 classes, and we apply the pipeline like I said before.
So it's 101 ways the classes.
101, yes,
Okay.
exactly. Okay, and if we look closely at on what Clip is classifying, it's not classifying just class names, okay? It's classifying a description of that image. So the assumption here is that by describing the actual photo, we can filter out some noise and make sure we emphasize on what truly lies in the image. Okay,
I think this one, they only had 5 or 7 classes. It says it there. One's in the bottom.
the bottom,
So I think, yeah, that's all you were saying.
yeah, it's 7 classes. over here.
Yeah, so there's 7,
Yeah,
angry face, happy face. So
It's 5 out of 7 over.
Right.
But the food is
that one is more,
100.
yeah.
Sun is 300.
So they generated the text saying a person, a boy with, or somebody with a photo. Happy something, see something.
Yeah, but Clip was, the important thing here is that Clip was not trained explicitly on those classes. So it's doing a good job.
Except for the last one, which did a really
Yeah.
bad job. No, it's more a sort of fine grained classification compared to a non-fine grained case. So I think that's what's the interesting thing is. So I don't know if talk about the food, they're probably very different types of food. So yeah, this is a question of what's interesting is fine grained to non-fine grained classifications. Maybe it's
text prompts are probably not ideal in this case for.
No, I think the clip itself might not be ideal for telling you something so similar. So you might just think about that in general.
Okay. So over here we can see a table that says zero shot Clip is on par with fully supervised ResNet 50 evaluation. And what we're comparing here is zero shot Clip with a linear probe model on ResNet 50. I'm gonna define what is linear probe. Linear probe is simply we take the pre-trained ResNet 50, let's say on ImageNet over here, okay? We take the pre-trained ResNet 50 on ImageNet, and let's take Stanford card for, let's take Food 101, because we already know that there are 101 classes in that dataset. So we take the pre-trained network on the ImageNet, and we add a linear layer or a linear classifier with 101 outputs. So it's simply just a classifier to the number of classes in that dataset. Okay, that's basically linear probing. We take, but it's important to say that we add that on a frozen pre-trained backend. Okay, so zero shot Clip is also that's the same setting like I said before, exactly like this. Okay, and we're comparing it with the linear probing. But the interesting here, like something very interesting happening, that if we look at ImageNet, which is the third one from the bottom on the green, okay, the test performance on ImageNet is actually greater on Clip from ResNet, which is pretty weird. Okay, we would assume that the opposite would happen because ResNet 50 was actually trained on ImageNet. And the Clip was not trained on ImageNet, it was trained on something else. And we would assume that the ResNet 50 linear probe classifier should surpass it here, but the representational base because it was actually trained on the representational based on ImageNet. But zero-shot clip even surpasses the ResNet 50 ImageNet encoder on the dataset that was trained on. So that's very strong, and that's very weird, obviously. And we can clearly see that the zero-shot clip outperforms the trained network on many datasets. Okay, so this I have to say this, emphasize on this. In order to get a linear probe model, we have to train. And zero-shot clip needs absolutely no training after the pre-training. On many datasets, we no need to training anymore. And another interesting observation here is that zero-shot clip actually lost on MNIST, which is one of the easiest tasks there is in the computer vision world. Okay, so this is just conjecture on my part. I want to see if any of you have any other observations, but I think the reason that CLIP can really perform well on real world data, but I think the reason that CLIP really outperforms ResNet 50 on real world data set because it was trained explicitly on descriptions other than the classes. Like the descriptions really make a difference over here.
The other way, if you look at the blues, let's say the Eurosat, I think these are satellite
Satellite
images,
image, yeah.
and it was not trained on them, therefore you have no idea what these mean. So the question you have to look at is, among other things, is what are these images, what do they look like? So MNIST, he wasn't trained on something that looked like the MNIST, on regular images. But the Eurosat is an example, he was not trained on that at all, so he doesn't know what satellite images are. So I think it's interesting to look at these data sets and see what they have and see what happens. Now the bird stuff, I don't know what that is, but if it's again what I talked about, fine grain stuff.
Flowers, fine grain.
Exactly. So you see so the two questions. Is it a type of images that he was trained on or not? That's the first question. Then fine grain, I think it has a problem. It's not accurate, it's not accurate enough. So we're recognizing sheep. That's what most people do. So that's what we're doing. And actually a ResNet worked better than a CLIP because again, all sheep are the same, but we're trying to identify them specifically. So I don't know if this is a rule, but basically fine grain stuff is more difficult because I don't think the CLIP will say, this is a sheep with a black spot on its head or something.
Not on Instagram, which is their data set. Like with the cars, there would be people would put on Instagram my Porsche versus my.
Mhm. Right, so the question is,
something.
what
It
the
depends on
text
what
looks like.
people put on Instagram.
It's not a constructed data set. It was trained on images from the internet, so it's probably what people actually look images.
And we'll give CLIP one of the classes as unknown, and it would put all the low confidence classes in that class. For instance, all the stuff here that it doesn't know, maybe it could place it in an unknown class.
Well, you can look at the probabilities that the
But-
CLIP gives you, then you can say,
Um,
if the highest probability is less than something, you could say it's unknown without even doing something.
Think of the pictures of just further away. Because it's just the nearness of the vectors, like what does unknown mean, like a picture of unknown, if you would never have that label.
That's zero-shot clip with zero-shot clip with linear probe, and now a more down to earth comparison is zero-shot clip with few-shot linear probe. Okay, so before we compared the zero-shot clip to linear probe, which means that we trained the classifier on the whole data set, and now we're going
Training set.
yeah, sorry, on the training set, I mean the whole
Because
class,
the result
the
of
entire
the
classes.
Like that linear probe before was training that classifier on the
The training,
training set
the
of the
training
data
set.
set and then evaluating
That's true.
on the test set.
Whereas here we compare zero-shot clip to few-shot linear probe. Okay, so the setting is different. There's not a classical supervised task. And here we simulate only having a small number of samples per class, which is where pre-training really comes in with its power. And we see that the zero-shot clips outperforms a lot of models if you only give them a small number of labeled samples per class. Okay, it's comparative to a 16-shot bit M on ImageNet, which is one of the best models that is successful on this transfer learning task. Okay, so we can see the I don't have my cursor, but zero-shot clip is the star, and the x-axis is the number of labeled training examples per class. So that's the k-shot in the setting. Okay, and the y-axis is the accuracy.
Does it mean that it's a linear probe in few shot?
It's a linear probe. It's a regular linear probe, like I defined earlier. Like the classifier classifies the entire classes of the data set, but the training set is very little different. Okay, so it's
Maybe I
not the
missed
whole.
it. You have the pre-trained model, let's say whatever is written there, the ResNet,
Okay.
for example, and then you have a linear layer
Mhm.
that embeds it into
Yeah, it classifies it. That's a classifier. We take the pre-trained ResNet that was, let's say, trained on ImageNet,
okay,
and we add a linear classifier,
and that classifier is trained only on
only on a few number of labeled shots per
it's
class.
trained with gradient descent, so it's not like
Yeah.
the ProtonNet trained.
Yeah, it's trained
Okay.
on
Okay.
gradient.
It's as if you take the training set of this data set, but you reduce the number of samples per class to 1 or 2 or 4.
But it says linear probe only on clip, and the other ones are linear probes as well.
Yeah,
Yeah.
yeah, they're all linear probes. They said because we have zero-shot clip and linear probe clip, we don't need just to make it.
What are all these gray things? Gray lines? What's a gray line?
The in between.
It's other models, no?
I think it's other, yeah, it's fair to say that it's other models, but those are the baselines, I think.
Yeah.
So the zero-shot clip, which is the star, they put it under like 0 number of labeled examples per class. We can see that it's on the same horizontal path line, sorry, as the bit M, and on the 16-shot. Okay, and if we actually use a transfer learning and create a train clip on 16 samples per class, it outperforms the bit M model by a large margin. Okay, and an interesting observation is that if we fine-tune the clip linear probe classifier on less than 4 samples per class, okay, so we can just tweak it on the left there, the performance actually decreases from the zero-shot clip. And it's pretty intuitive if we think about it, since the clip classifier was trained in a contrastive way, it classifies based on text similarity. And if we use the linear probe method, we need to throw away that last classifying layer and replace it with an old school classification layer, which is different tasks than a different task on what clip was trained on. Of course, that layer needs training, and the conjecture here is that maybe 1 shot or 2 shots until 4 shots is not really enough to do that like it should. But it recovers on 4 shot, and so we can forget.
You should mention that there's linear probe clip uses only the visual encoder, not the text
Oh, yeah.
encoder as far.
And the linear probe over here only uses the visual encoder. So the text encoder is used as is, and we only add the classifying.
I think it's not used.
Yeah, what is the text encoder used for?
Oh, sorry, yeah.
Zero shot is, but in the linear.
Sorry,
Yeah, right.
yes, that's true. We only take the visual encoder from clip over here and we adapt it with the classifying layer. So the text, we throw away the entire text encoder.
So the zero-shot clip is the only one here that knows the names of the
Yes.
classes.
Yes, that's true. Exactly. Okay, so this is clip. And we're gonna improve upon that by,
So I'm sorry, it's actually, what this means is that the distance to the text embedding of this class name
that distance between the text.
between the pictures and the text embedding is smaller than the distance to other members in your class, because the one shot and the two shot and the three shots, they're like to other members in your class. So like the distribution within class, like somehow the text is placed in the middle. So that, right, because this is what it means that the,
Yeah, you have a lot of noise in this.
If you only have 2 or 4 examples per class, they don't describe the distribution so well, right? So a new image is not necessarily close to them, and
so you're saying that if they used just a distance instead of a linear probe, like a trivial linear probe, maybe it would do better. Like the 1 and 2, you're hitting the failure of the noise rather than of the embeddings, that it's not so good.
what do you mean by just the distance?
That in the one shot, you could take the, say one shot, you could take the one example you have and look at the distances to it. Right, like in the 0 shot, you're looking at distances.
Yeah, I think it's almost what happens when you train a classifier.
Exactly,
Right,
what can it do apart from take a distance?
Yeah,
So,
but
I mean, it's
so
not
my
correct.
assumption, it didn't learn, the linear probe didn't learn any meaningful weight. Like the,
yeah, it needs a large enough support to learn something meaningful. As far as I know from other readings, that the text and image representations are actually not
on top of
this,
each other.
yeah, they're not on top of each other. They're, I mean, the text for a certain class will be closer to images of that class compared to images of a different class, but they're not, they don't actually live.
Wait, why do you say, like, where do you know this from?
Discussions with Daniel, who's not here, fortunately.
The reason I'm asking is when we did this training,
Mm.
it's like spot on.
Mm.
And-
It was a good manual, like
No, no
here it's
labels.
to be expected when you invent some label that's like whatever of a cat.
No,
you-
but,
And you want to expect
Ah.
it to label the.
no, but you can look at the labels and images of your training data and see if they overlap with each other. You expect them to overlap.
Yeah,
Now,
so-
other sentences which are close enough should overlap with the sentence,
Mhm.
like it's supposed to. Like, this is what your loss function gets you, no?
Yeah, but
And in our data, it's like spot on, like,
here the embeddings come from 2 totally different kinds of networks, right? Is that the same in your case? But
it's 2 modalities, yeah, the one is text, one is images. and ours is
but
two
also
modalities.
the networks themselves. One is a ResNet, the other is a text transformer.
It could be
so-
the
so-
visual transformer, then it's not completely different.
But
Ours are transformers, both of them, but I'm not sure it makes a difference.
no,
the-
but the text is, you know, could be, the descriptions could be very different text of the. You know, photo, the thing is, what could be the description of this image could be something much more, with more details or other things.
It's a huge data set, like, oh, this is supposed to move away in the noise and the averaging.
What you said was about the support of the. Like what the labels that you said did not sit on the images.
In general,
Or labels,
after
or-
you have if you take a pre-trained clip and just run it on new data.
A new data.
Yeah. Yeah.
So that's
right.
like the generalization. that
Yeah,
it
yeah.
takes in.
So
Okay, so
the
maybe
way it
the-
generalizes, I think that the images will be closer to each other and text maybe not. Cross. That's what I heard. I don't know exactly.
Cause it's supposed to be. like the loss function pushes it to
Yeah.
be the same space.
Yeah.
Like what you're describing
Yeah.
as some failure.
Not
No, on your
necessarily.
deck.
It's supposed to be closer to the right text
And the other
than
one.
the other ones, but not in the same,
No,
not supposed to be close.
it is supposed to be close because you're doing the cross entropy on the lines and on the thing.
Yeah.
You'll get this
But
when
how
it's,
close?
when it's on it, like the loss would go down. If you could do this or this, you're better off this because the loss would be pushed down.
Sure, no, if you have like two, they are exactly aligned, but on a different, like in one dimension, they have offset of one.
No, but you're measuring the cosine distance between these vectors and these vectors. You're better off placing them on top
Yeah,
of
you're
each other.
better off, but maybe it's
And you're
so difficult
totalizing them
to.
first, like you're better off placing, the loss function pushes them to be next to each other.
You're right, but maybe it's so difficult to achieve.
Maybe it's too
during-
difficult to achieve, but the loss function pushes them to,
But the
Yeah,
problem
let's
is,
say,
it doesn't happen on the train, the examples on which it was trained, or new examples, that's what I'm.
So I think on
saying,
new
for
examples,
New
yeah.
examples and the labels are much simpler than labels from Instagram captions. To be
Probably,
exact.
but probably it's closer then. Of that
Close.
close, that's the.
Like just 101
Yeah.
labels from the woods.
no, so generalization I see, but the,
Yeah, I'm not
It's supposed to be-
sure. Yeah, okay, let's go on.
I think it's interesting to compute. You were saying, let's look at, you talked about, to say the unknown class, so let's see if the best score is lower than something, then let's say we don't know what it is, that's what you were saying. I'm not sure that's, what happens is, I think more to look at the softmax values and say, get numbers, so they might not be that close, but if you get similar probabilities for many classes, that means we don't know what to work, we don't know, it's not the number itself, it's more. Because again, these are very high dimension stuff, it's very hard to understand what's going on. So I don't think they're that close, but they're closer than the wrong ones, that's what usually happens.
So before we continue the adapters, I just want to make sure that everyone understands. The few shot learning setting here is, okay, let's say we take 4 shots. So we take and we train for, let's say, 300 epochs or something. So we take the same 4 shots every epoch from each class. There's no,
yeah, of course.
otherwise it's cheating, yeah, exactly. So, yeah, this.
And I don't think you need 300 epochs, this is
Yeah.
the
No,
one,
it's just,
no, I'm just saying, no, the numbers of epochs is
Actually, no, you need.
5.
You need,
You need-
you need over here, yeah.
We're just trying doing the last one level of the network.
Yeah, that's true.
I'm just saying, again, I'm just saying it should be an easy, maybe it doesn't work, but it should be a fast training file, this file.
Okay, so now we're going into adapters. I'll be talking about clip adapters, to be more specific. And it's basically a lightweight module that allows us to repurpose clip efficiently with minimal updates and very strong performance. And we'll explore the architectural designs and the trade-offs that the authors address in this paper. But let's talk about what an adapter is like before we talk about clip adapters. Adapters were introduced as a compact and extendable module that adds a few learnable parameters to the network architecture. They added it, the first adapter was added in the paper parameter efficient transfer learning for NLP in ICML 2019. And they were added to an NLP task to the BERT architecture to attain a near state-of-the-art performance on 26 NLP classification datasets. And it's very trivial to see that as we push for task-specific performance, fully fine-tuning clip becomes impractical. Okay, so both computationally and in terms of storage, of course, because clip is very large. And we can see that basically the adapters are just MLPs. They present linear transformations with residual connections. That's the and we can since we have 2 encoders for clip, we can apply an adapter for each one of the visual and text encoder, one adapter for each, and followed by that residual connection, which is controlled by by a hyperparameter per residual connection. So one for the text and one for the visual. So we basically take a certain percentage of that residual connection. And we can think of an adapter as a simple autoencoder where we downsample the input and then upsample it again. And each adapter has its own learnable parameters and they are not shared. Each encoder has its own parameters to learn. And we add the newly learned knowledge by the fine-tuning via the residual connection. But the important thing here to address is that we have to keep the backbone frozen. Otherwise, there's no sense in it.
So the network is two layers. It's just two layers.
So it's like two linear transformations with a activation function.
Leaves the number of parameters the same. The input and output.
The backbone,
The output of the backbone and the output of this thing is the same length.
yeah, exactly.
Where is it at the end?
We're gonna explore adding it in different regions, but basically it's added at the end. Okay, the flip adapters achieve the best performance when they're added at the end, but there are also works like now where they're added in between the layers. Okay, so that's firework. Excuse me for my brief understanding, but this slide was added an hour and a half ago. So on the left is the architecture of the 2019 ICML paper. And this is the architecture of the NLP adapter module and its integration with the transformer architecture. So if we look at the left figure in the left figure, we add the adapter after the feed-forward layer, after each feed-forward layer, to each transformer layer, and after the projection, following the multi-head attention, and after the two feed-forward layers as well. And this is just like if we zoom out, that's where the adapter is. But what is in the actual adapter? That's on the right. The adapter consists of a bottleneck, which contains few parameters relative to the attention and the feed-forward layers in the original model, and it also has a skip connection, as we can see from the entrance to the exit. Okay, and the green blocks are actually the train blocks in this. So we simply learn the adapters and the normalizations in the transformer layers. We don't relearn the attention and the MLPs in between. We just need to learn this adapter, which is a small module compared to the large network, and the normalizations as well.
Where do you see the normalization?
Sorry,
What you call the normalization?
the layer norm in the left figure.
Ah, the green, okay. You have like this in it, okay.
Okay, so the adapter is the one on the right. Like if we zoom in on the yellow, we get the right figure. And this is the NLP task. And then they added it to, it has like, on the right, we have the vision transformer adapter, which is a bit more complex from the NLP one. If I can just zoom a bit, but given the image, okay, we can think of the above line as the regular vision transformer, and on the bottom we have the adapter. Okay, so the vision transformer is completely frozen, we don't touch it, but the vision adapter is a bit different from the NLP one. It has three main compartments. The first one is the spatial prior module, okay, which is just downsampling the image. Okay, but why they added it, as I understood, because the patch embedding, like it splits the image into a lot of patches. Let's say it's 16 over here. Okay, so it loses its spatial what do you say? Spatial yeah, and this spatial prior module actually learns a bit of features that is lost during the patch embeddings on the actual image. And the injectors, which is the yellow blocks on the right figure, this is optional, but they take they simply apply cross attention, and the query over here is the output. The query is the output of the vision transformer, and the key and value the key and value values are actually the outputs of the adapter that they get it from the adapter, and the queries they get from the actual vision transformer. Okay, and that goes into the extractor. That's the third main compartment of the adapter, and they actually switch it. Okay, so the key and value is actually the output of the block in the vision transformer, and the query is actually the output of the cross attention in the adapter. Okay, so this paper is really like large. We can assign we can talk about it for 2 hours, but this is probably work for the adapters. What we want to talk about is how we can use it to leverage Clip's pre-trained knowledge and get even better performance on few shot learning. So yeah,
In the case of the NLP adapters.
Yeah.
So those two instances of the adapter have the same weights, or is it different weights?
no, they're different ways.
Different weights.
They're different ways, yeah.
And I see. So essentially, so when you said the best performance was to add the adapter at the end,
This is not in this.
it's not.
It's not in. It's
Okay,
not in this
the-
market. Okay, so the clip adapter actually improves upon on this paper over here, which is called co-op. I call it co-op. If it's scoop, I don't know. But what they suggested in co-op is context optimizations. So it's actually learning the prompts of the. They ask whether learning the prompts for the clip is actually better than assigning the manual. Okay, so if we look, for example, at Flowers 102, the prompt that clip gets is a photo of like, let's say, lavender or something. Okay, so I don't know flowers. So it's a photo of a class.
So what is it?
A water lily. No, בראש, lavender.
It's serious about it.
And so context optimization, they said, okay, let's learn the prompt. Okay, and there are multiple ways to learn a prompt, of course. And maybe that gives us a better representation of or a better semantic relationship between the actual photo and the text embedding at the end. Okay, so they tested it over here on the few shot on the few shot setting, and it's the same one as in the one that we talked about before. Okay, we have 1, 2, 4, 8, or 16 shots of the same samples in every training episode, and the different configurations that they tried over here for the length token is that, of course, the length of the token that's going to be, and the placement of the class inside the token. So if we look at the photo example again, we can see a photo of a class. That's the basic one. The learned one is a photo, a flower photo of the class, and the last one is a photo of a class, a type of flower. So the placement of the class can be either at the end or in the middle. And of course, the length of the token of the string is also has impact. And the best configuration that they found is if we put the class in the middle and the token length of 16. And they also made it class specific. So for each class, we have a special prompt to do for that. Okay. And in Eurostat, for example, they found the best way to address it is a centered satellite photo of class. So they put the class at the end, and will also, I think, a token size, a token length of 16. But this is a bit time consuming.
But the way they do it, they train on each data set.
Yeah.
A transformer that outputs this prompt.
No. It's class. They train it on each data set, and the learned prompt is class specific. But the way they do that is that they, okay, let's say if you look at the left figure, where there's ice, it's frozen, where it's fire, it's learnable. So we push the photo in the visual encoder and the regular and the prompt in the text encoder. We make a prediction, okay? And we use backpropagation in order to learn this new prompt. Okay.
So it's actually related to what you asked before, right? So
Yeah.
you take here 10 images of a dog and learn one sentence that
I mean,
is aligned with them.
still, you will still limited to discrete classes, but it's meta.
Yeah.
The tokens are discrete now. How can you train them with gradient descent?
No, it's like a learnable token. Maybe I don't understand the question.
So the learnable part is the embedding of that token, but then does it correspond to a word?
Okay, so they said in the paper that they have, like I said, different configurations. So they did assign, let's say, for the flowers data set, explicitly put please the name of the class in the middle. Okay, so maybe that answers it. Like it's very data set and class specific. For example, for your set, they still put the class at the end. So it's not entirely learnable. They do have configurations. You can assign the placement of or the position of the class, like where it should, and what's the token length per data set and per.
Yeah, okay.
Okay,
But then the words themselves are
learnable. Yeah, they're learnable.
That part I'm not sure I understand how it is.
But maybe there's a small network that generates the sentence, which has parameters that you update and then.
Okay, so the task now here is basically a classification task, right? So we use the cross entropy loss and minimize that for the task. But the problem here is you see the gradients have to flow backward through the entire text encoder in order to get to the token and learn it. Okay, so that is that's computationally heavy, and that requires a lot of memory because we need to save all of the values. So on total, to learn the prompt, it took 14 hours and 40 minutes, which is a lot. And the question here is, how can we improve upon that with minimal time? Okay, so the answer here is adapters. Okay, so just gonna we'll show you the illustrations so everyone can have a clear understanding on what F is and what W. Okay, so F over here is the visual embedding when we push the photo in a certain model. Let's say it's a CNN or a vision transformer. And W is the classifier weight. That's the naive classification. We multiply and we get the classification. In CLIP, W is actually the embedding of the text. Okay, so we also multiply that. We get the cosine similarity and we classify. In co-op is the same as CLIP, but with a learned. It's with a learned prompt. So it's exactly the same pipeline, but the prompt is different. Okay.
Wait, again, in co-op,
In co-op, it's the same as CLIP. It's the same as CLIP classification, but with a learned prompt. So it's not a photo of a dog. It's actually a 16, let's say, length token, and with a dog at the end or in the middle, depending on the class and depending on the data set. Okay. And this is the CLIP adapter. Okay. So, like I said before, CLIP, the adapter is basically a linear transformation. It's basically two linear transformations, an autoencoder. And first we have an image and a prompt like before. Each one of them goes through the relevant encoder and returns an embedding representation. So F is the visual embedding and W is okay, so here it's the same prompt as clip, okay, it's not the learn like code, it's the same one that clip gets. And it returns W as the embedding matrix of the text. Now each embedding goes through an adapter of its own, and we get a transform feature. And we add the residual connection and we check the similarities again.
But in the expensive one, they didn't have a visual adapter. First, like in
B?
the 14-hour thing they had, they
They
only
didn't.
had a text adapter, so to speak.
No, they didn't have any adapters at all.
No, it wasn't an adapter, but they were changing, like the degree of freedom was only at the text
Mhm.
level.
Yeah.
And now they're adding like an extra degree of freedom.
Okay. And during the training, the weights of the adapters are optimized with the contrastive loss following the original clip. Okay. And where W, where the W's are the MLP weights and N is the batch size. So we have 4 learnable matrices basically. Okay, and let's not also forget about the percentage-wise residual connection.
But,
Okay.
but whatever optimization they had, they didn't clip on a large data set. Like, why would this work? Like, what they're doing is like a clip adapted for a specific data set, like this is like they're adding a specific data set for the. tuning.
A few shot, but with few
Ah, but with
labeled
fusion.
with
Yeah.
few
And the
labeled.
adapters will change based on the fusion, like it's a better fusion.
Mhm.
Okay, I'm sorry, I understood.
That the clip is frozen and they never have to even propagate through clip. That's the.
Yeah.
Instead of fine tuning clip, you add like member clip for that.
Not even a minute clip, it's negligible. Very small number of parameters.
No, it means mini clip in the sense that the loss function is clip like.
Yeah,
this.
Yeah,
The
yeah.
last function is split. It's the same one as split.
And here in the drawing of the adapters, it looks to be, sorry.
It's no, it's
just sideways.
yeah, it's
okay.
sideways. Okay, so interestingly enough, there are a couple of, when we said there's an adapter for each one of the encoders, we can investigate the variance of the clip adapter. Okay, since clip adapter has three structural variants. Either we have 2 adapters, one for each encoder, and we can add or remove one of the latter or add both at once, right? So we can, yeah. And they tried that, like the authors tried that, and interestingly enough, the visual adapter alone gets the highest accuracy. Okay, so we
Maybe
can,
this is what. Maybe this is what. The gossip that made it to me
yeah.
as big.
Mhm.
So we can conclude that the text adapter and the visual adapter perform comparably and both improve the classification accuracy over the zero-shot clip. But adopting the visual adapter alone works much better than adopting both adapters and the text adapter alone. This indicates that it is more important to conduct image feature adaptation than text feature adaptation. Okay, so maybe the visual representation of clips can really be improved. And since the semantic gap between the visual images in the pre-trained and the fine-tuning dataset is larger than that of the text features, maybe it's better to just adapt it in the visual sense. And it's very surprising that combining both adapters really it like harms a bit. It harms the accuracy. We don't expect that, but it is what it is, I guess.
But it's almost the same, like,
Yeah,
we
almost
wouldn't
the
make
same.
any
It's almost the same.
conclusions from it, it's almost the same.
Yeah, but
So why bother with it? I mean, there's no good reason to.
No,
use-
I see this, but it's just a few parameters.
okay. So the clip adapter, the experiments were done on the 11 data sets, 10 were fine-grained datasets, like Elon said, and one of the datasets, like the 11th dataset, is the ImageNet dataset. Okay, so Clip Adapter outperforms the other 3 baselines that they use. First off, we have zero-shot clip, a linear probe clip, and the co-op that I said, or that I explained before, and it improves upon all. Okay, even on different few shot settings. So even under extreme conditions such as 1 shot or 2 shot, it it even outperforms the 0-shot clip. Okay, which is we didn't have that before.
They took only the visual adapter in this one?
Yeah. Over here, since adding the visual adapter yielded the best results, so they only adapted the visual adapter here. Only added the visual adapter. So yeah, even the average over the 11 data sets, it improved upon 0-shot clip. I'm going to say that for 5 data sets, Clip Adapter achieved huge performance boosts ranging from 20 to 50%. Okay, and the improvements become smaller on more challenging and generic datasets. So it really yielded the most results on the fine-grained datasets. Okay, and on the generic datasets such as Caltech 101 and ImageNet, it got minor improvements. It's not as large as the other ones.
Why do you say that it's minor? Looks big, like it looks bigger than the 102.
Yeah, but it's not 50% boost or 40% boost. You know what?
So Flowers
You're
102,
comparing
the
it-
boost is from 62 to 72, maybe
Yeah, that's
10%?
also minor improvement.
Okay, and the Sun 397, it's like 7%, you would say?
From the 0-shot, right?
Yeah, you're
Yeah.
talking about but in the Caltech 101, it's more.
Mhm.
So it. You say that, which is
It's 27% boost on imaging.
in ImageNet,
Okay,
it's 27%, but it looks like 6% or something. 5%, no less.
so for the fine-grained data sets, it got minor improvements, and for the generic data sets, it got a huge improvement. Maybe maybe I switched between them.
ImageNet is like 4%.
ImageNet, no, it's 27 boost from the linear probe.
From the linear probe.
Linear probe again doesn't use the
Doesn't
see the- linear probe doesn't have the text, the label.
And compared with the co-op method, that has already gained huge improvements over the 0-shot clip, Clip Adapter still outperforms co-op on all data sets and on all the different few-shot settings. Okay. And note that Clip Adapter handles the few-shot learning from a totally different perspective. Okay, just remember that in the Clip Adapter, we fine-tune the model, where co-op we prompt tune. So maybe it's different. It's a bit different over here. Okay, so this suggests that fine-tuning lightweight adapters with some residual connection for prompt fixed pre-trained vision or language models can achieve better performance than actually prompt engineering or manually prompt tuning the text. Okay, so this has huge bonuses aside from the performance boost, like on the accuracies. If we can look at the figure, if we can look at the above figure, let's talk about efficiency first. Okay, so in co-op, we needed to backprop through the entire text encoder in order to get to the text tokens. Whereas here we only fine-tune the last layer, so it's much less time. Okay, if we look at the,
Is a different group,
it's,
or it's them?
no, I think it's a different group.
Okay.
Okay. And if we look at the table below, Okay, so zero shot clip is not really, we can't really compare over there because there's no training. But the linear probe clip was trained on 13 minutes with about 1 million parameters. And the GPU memory over the dashes is like the same. It's the same inference speed and it's the same GPU memory. Co-op needed 14 hours, okay, so we only tweak the prompt over here, so it's very much less parameters, okay, but it needed a lot more storage because we need to save the whole parameter while we back prop, and the inference speed is a bit larger because we have a larger token. Okay, the clip adapter only needs less than an hour of training time with half as much parameters as linear probe clip, with little to no memory additions at all. Okay, and the inference speed, like the 0.4, is pretty negligible over there. Okay, so the adapter is very negligible compared to clip, so it's a very good, nice addition.
How did you say how the prompt is chosen in the clip adapter?
Prompt is the exact same prompt as they use in the clip train, like a photo of a dog. Photo. They don't play with the prompt. So.
But actually, they could have done like prompt engineering, like once they're training this mini adapter network. They could have added, like, instead of 4-shot, they could have gotten like for free. Like it's a trivial augmentation technique, like to do
Oh,
more
yeah.
prompts, more like augmentation on the text, augmentation on the.
Use the co-op and the adapter.
No, the co-op is like it's a complicated how to get these prompts, but the prompt engineering, a photo of
Oh, manually.
places, yeah,
selected.
like
Okay.
just the boilerplate, but
Yeah.
like many. It just spreads the vector in
Mhm.
the embedded space, so to speak.
So since the visual, so before we get the different backbones, and I remember who asked me here where they inserted the adapters. So of course, the most intuitive way to think about adding the adapters is on transformer blocks. So the experiments were conducted on the Vision Base 16 Vision transformer, and the experiment was done on the ImageNet using 16 shots. Okay, so we have 12 layers of Vision transformers over here, and the numbers is after which layer, like after layer 0, we we add the adapter, or after layer 2, 6, 10, and 12 is the last one, and all is where we add after each layer is after each layer of the Vision transformer, we actually add an adapter. Okay, and we can see that adding on the last layer yielded like the most let's say most humbling results. Okay, so we had
Can you explain the
worst. What I just explained.
Like, I
Okay.
don't understand what the. Yeah.
So this table over here, the above table, it's the table above showcases how can we add adapters in a different way on the backbone of a visual architecture. Okay. So the intuitive way to think about it is if we get a Vision transformer, and so we can add the adapters after like a certain Vision transformer block. Okay. So insert layers is after after which layer we add the adapter. So 2 is after the second layer, 6 after the 6th layer, and 12 is the final layer. Okay, so that's the those are actually the results of the experiment, the 12th layer. And all is we add after each transformer block. Okay. At the end, they decided it was best to add after the final layer, maybe because the number of parameters is so low and we don't need a lot of memory. But even if it harms a bit the accuracy, it's not like we can delete that.
What about no adapter? How would it?
How about what?
If there was no adapter at all? How would it?
It's basically zero shot clip.
Yes, but so how much was it? I don't remember.
Okay. This
So it's just 55.
it's like 2.2 gigabytes of memory. Okay, so it's
But like the improvement just from the adapter is 20%.
oh yeah, that's on ImageNet 16 shot.
Yeah.
That's not what you see in the picture.
Linear probe where
Linear probe, you're right.
Yeah, they're doing the linear probe.
Linear probe with 16 shots, it's like a different point.
You need to compare a few shot setting with a few shot setting. You can't really compare to the 0 shot clip. And
How
the
come the parameters change if
Okay.
you, where you add it?
Sorry?
Why does the number of parameters change depending on where the adapter is added? Like what difference does it make
Oh,
where it's added?
No, the number of parameters is the same. Like, oh, maybe it's the transformer block. Maybe
I have different dimension.
yeah, exactly. Okay, so all is basically when we add the most, we have the most parameters. So it's not really, it's not really good. And the question is, do adapters help all different visual backbones, like also convolutional neural networks and vision transformers as well? And the answer is yes. Okay, so it does. And over here they compare it with CoAP on 2 datasets, the BTD and the ImageNet. And you can see that there's an improvement on the clip adapters when we get a Resonant 50, a Resonant 101, and both vision transformer backbones. Okay, so it really does help it in that manner. Okay, and so what about fine-tuning the clip encoders alongside the adapters? That's also a question that we need to answer. And over here, where we see a check is actually this part is unfrozen in the architecture. So the first row is just basically the adapters. The whole clip is frozen. We only fine-tune the adapters, and we get state-of-the-art. The second row is if we also tweak the visual encoder, it actually harms it, but it takes a lot more time to train. Okay, so it takes like about half an hour more because we need to also tweak the parameters of clip. And it seems that the text encoder really harms the performance of it and the training time as well. So it's not able to do that. So the best answer is to just train the adapters without the touching clip. Okay. So until now we
just
oh,
I'm
10 minutes, I think it's in.
Mhm.
Until now we talked about training an adapter for the task at hand, and these are the same authors. They published. Okay, so the 2 papers were actually in the same year. They're published in the same year, but they were accepted like a 2-year difference. I think the adapter was accepted in 2021.
I think they both appeared on archive in 21, but they were accepted in 23, 24.
Yeah, so they took like 2 years to get accepted. And what they proposed here is if we can, they asked the question, can we apply a transformation so that we don't need to train like the transformation at all? Can we apply a deterministic transformation instead of the adapter that yields us comparable results? And the answer is yes. Okay, so they said we propose a training-free clip adapter. It doesn't need any backpropagation, no training whatsoever, and it creates the weights in a pre-processing manner when we get the training data set by utilizing a key value cache model. Okay, so it's similar to an attention, an attention equation. And it can be improved further by fine-tuning for a very, very small number of epochs. So it's like an 80% initialized adapter. Okay. Okay, we have k shots from n classes for a few shot task, and we need to create this key value cache model and convert it to something that we can use. And using the visual encoder, I'll show the figure in the next slide, but bear with me. Using the visual encoder, we push the entire training dataset in that visual encoder, and since we have n classes from n k shots, we get n times k vector representations. Okay, we can concatenate that and turn it into a matrix. And we call that F-train. So F-train is basically all of the outputted features from the training set. And it's a matrix the size of n times k, and c is the latent space dimension. Okay, and L-train, that's actually, since it's a few shot learning setting, we actually have the labels. Okay, so we construct the L-train, that is the labels. Okay, L is for the labels, by converting each label into a one-hot encoding vector for all of the n times k samples. Okay, and
It's
that
by C, yeah?
What?
NK by C,
is F train, yes.
L train.
L train, no, it's
NK
times
by-
n because it's one-hot encoding. You need all the classes. And the-
Result is an vector.
let's put on the cache model for k less than 16. I'll talk about in a bit. But this is the illustration, and let's take a look at the above. Like, just let's see the visual encoder. Okay, the few shot images. This is n times k. Okay, so we push each one of them into the visual encoder, and we get a feature representing that image. Okay, so we have, let's say, n classes, and they sorted over here so we can have a much easier look like on what it does. It's a C. It's a matrix with rows of C and n times k samples, and it's just simply a concatenation between all of the features that are the outputs of the visual encoder. And we have the one-hot encodings for the labels in the L-train matrix on the right. Okay, and they sorted it in a nice way so we can really see it clearly. And at inference time, since it needs no training whatsoever, we just need to talk about the inference. We get a test image, we push it to the same visual encoder, and we get a feature, right? And what we do is simply multiply that feature by the F-train matrix, and then we apply a certain transformation or a certain function. Okay, over here it's an activation function, but they specifically, I'll talk about in a bit. So they apply an activation function, and then they multiply it by L-train. Okay, so that really is like the same thing as doing an attention, but with different matrices. So we can think of the F-test as the query, and the F-train as the keys, and the L-train as the values. Okay, that's like the key value cache model that they talked about. And of course, we should not forget about the residual connection. The residual connection is made by multiplying the transformed feature by a hyperparameter, and adding on it F-test, which is the visual embedding of the test image, times that WC. Okay, so that's the classifier weights of the clip. Okay, so we still utilize that.
Isn't that the same as if you do prototypical networks? We
Like a near
look for the closest
Similarity. Yes, for the similarity, exactly. Yes. It's really like, it's really the same thing.
זה one, אתה מכפיל אותו ב-L ואתה מקבל את השורה המושכלת של ה-L.
אילן צודק פה.
Yes.
Oh.
Yeah, yes, yes. There's the paper where they actually apply prototypical networks on clip in a few shot setting, but I end up not. Didn't want to do.
Where is the adapter here? I don't understand.
Okay, so the adapter is, like we said, the adapter is basically a linear transformation, right? So we construct a deterministic linear transformation by doing that in the pre-process that we do. And that's basically the adapter. That's the linear transformation.
After that is a function of all the classes, all the few shot classes.
Yeah.
Not only single example.
לפחות,
Trained based on this.
Exactly. But this is comparable results. It didn't correct it didn't like keep state of the art, But like I said, just a minute over here, I'll walk back to that. They introduced a variant called tip adapter F, which is fine-tuning this transformation for a bit for a very small number of epochs based on the number of labeled samples that we have over here. So it's the same few-shot setting that we had before. Okay, but since this is already an initialized, this is like a really good initialized adapter, let's say. Okay, so the amount of time that it needed was like 5 minutes to train, and it really achieved state of the art over the others.
Okay, first applied the adapter, and then they train.
Training? Yeah, exactly. Mhm. And if you can see at the right figure, the right table, the tip adapter, like it didn't really go over the clip adapter, but the fine-tuned version improved upon it for a bit. Okay. So that's the figure over here.
But I just want to insist that this means that it falls one on top of the other. Otherwise, this wouldn't have worked. Like it's like the distances when you multiply it one by the other. This is what, like, you're getting the. This means that that it falls one up, that the generalization is fine and. No, this is a. Not your intuition.
That is closer to the correct
Yeah,
class
yeah.
than it is
It's
to
just
another
like
class.
Yeah.
So it does generalize in that way, but not necessarily that the text and image encodings are.
No,
Or
it does,
of each
because
other.
if you go to the previous. No, no. They can. Okay. That's what they.
So I'm just gonna end the presentation with this for out of time, because this is very important, like for the training free clip, a clip adapter. You can see that comparing it with the actual clip adapter, it only needs like 5 minutes of training time because it's already initialized so good, and we only need like 10% of the resources that clip adapter needs, and it also gets a better accuracy. So that's a win-win for everyone. And they compare it with multiple visual backbones as well, like they did with a clip adapter, and they still find out that fine-tuning this training free clip adapter also improves on the accuracy of like on all of the backbones. So that works. The ablation over here is really strong. Okay, and of course they do that on the we see much similar performance on all of those data sets that they use in the clip linear probe and clip adapter, and it improves upon all of them really. It doesn't lose it doesn't lose at all. Okay, so yeah, I think I went 2 minutes, 3 minutes over the. But yeah, that's
I wonder, by the way, what would have happened